Hi, welcome to another episode of Holyfield Physics TV. Today we're looking at wave diffraction, which is for the Year 12 Electrons and Photons course. First up, let's look at a single wave. Direction of the energy transfer is at right angles to the direction of particle oscillation, so we've got a transverse wave. To find the wavelength, we can just measure between peak to peak, or more precisely, between 2 points that are exactly 2 pi out of phase. Let's look at lots of waves travelling together. And this is the sort of thing you might see at the seaside, at the beach. You're standing there and you're jumping over the waves. You're not jumping over a single wave, but you're jumping over lots of waves all travelling at the same time. And so what we're really jumping over are those red lines, which are lines that join the peaks of our waves. And those lines are called the wave fronts. Now, as you can see, the wave fronts are at right angles or perpendicular to the direction that the wave is travelling, the direction of energy transfer. We have two different types of wave fronts that we can look at. The first is the one that's shown now, which are plane waves, and they're all perpendicular to the direction of motion, and they're all travelling in the same direction. The other type we can look at are circular wave fronts. Here we've got the wave fronts springing out from a central point, from a single point, and the waves themselves are travelling in all directions. And you can imagine this being a raindrop in a puddle, or someone dropping a stone in a pond, something like that. Wavelength is just the distance between consecutive wave fronts. Let's have a look at the waves as they travel through gaps. So here we've got some plane wave fronts, and they're going to pass through that small gap. What we find is that the plane wave fronts are turned into circular wave fronts. Waves are spreading out from the gap itself. Now, the amount that they spread out is determined by the relative dimensions of the gap and the wavelength itself. If the gap is smaller than the wavelength, then we'll have perfectly circular wave fronts, all the waves spreading out, and the gap will act as a point source. This spreading out of the waves is called diffraction. Now, if we've got a gap that's slightly larger than before, we'll still get some diffraction, but most of the wave that passes through the gap will carry on being a plane wave, and we'll just get diffraction at the edge. So we've got less diffraction occurring this time. And as you can see, the gap is much larger than the wavelength itself. Now, this effect occurs for all different types of waves, from light waves to sound waves to water waves to microwaves to radio waves. All of them suffer from diffraction, but the longer the wavelength is, the more obvious the effect is. Now let's look at two waves that pass through each other. What we're going to try and figure out is exactly what happens at the point where the two waves are passing through. Well, the answer to that is determined purely by the waves themselves. Firstly, the frequency of the waves, secondly, the amplitude of the waves, and then thirdly, the phase difference of the waves at the point where they're meeting. But whatever happens, they will certainly interfere with each other. In other words, they will produce a combined disturbance. So how do we figure out what that combined disturbance is? Well, all we do is add the waves up. So we'll take a moment in time and look at first wave and then the second wave. So we've got the blue arrow and the red arrow, and we add those two up, and so we get a slightly higher part of the wave. Look at the next section, hardly any blue arrow at all, bit of a red arrow. And the more of these that you do, the more samples that you take, the better your results are going to be. In the end, we end up with this wave being formed. This time we've got two waves, both with exactly the same amplitude, both with exactly the same frequency, and they're crossing each other completely in phase. So we're always getting peaks from each wave arriving at that crossing point at the same time, and similarly troughs from that wave, each wave arriving at the same time. and we'll end up with a bigger wave. This is a special type of interference, and we call it constructive interference. So what's needed for constructive interference is that we've got the same frequency, the same amplitude, and that both waves are in phase. Let's have a look at these two waves. Now, as you can see, there's a difference here. Each time a peak arrives from the top wave, it's being met by a trough from the bottom wave, and vice versa. And this time we'll end up with no wave at all. Now, this really is a special case of interference. This is called destructive interference. Again, we've got the three things that are most important here. Firstly, same frequency. Secondly, absolutely vitally, same amplitude. And thirdly, the two waves are antiphase, or out of phase by pi, or 180 degrees. We can put all these ideas together and look at the two source interference pattern. A bunch of plane waves coming up to two gaps. Because the gap is smaller than the wavelength, we're going to get circular wavefronts on the other side of the gap. As you can see. But we should also be able to see is that where those dotted lines are going to be regions where peaks are always meeting peaks and troughs are always meeting troughs. In other words, along those three dotted lines, we have the two waves, the red and the blue, completely in phase with each other. And so we'll get, on those three dotted lines, constructive interference. Halfway between each one of those dotted lines, we'll get perfect destructive interference. Now we know this because the two circular wavefronts that are being formed have been formed from the same set of plane waves. We can do this with light, and we'll get light and dark fringes, as you'll see in Young's double slit experiment. We can do it with sound, and we'll get loud and quiet regions. Do it with microwaves, with high and low intensity microwaves, and with water waves we'll get rough and calm regions. Another way of looking at this is to figure out exactly how many waves we have. So for that first bright fringe, the top wave has got 1, 2, 3, 4, 5 wavelengths. But the bottom wave has got 5 plus 1. So the path difference between the waves from each slit is pi. Now this is the requirement for constructive interference, a whole number of wavelengths in the path difference. Now if we have the distance between the screen and the slits as capital D, the separation of the slits is S, and the separation of the bright fringes is X, we'll get lambda equals Sx over D. This is a great way to work out the wavelength of light, because we can use this experiment using laser light, find those fringes, measure S, X and D, calculate the wavelength of the light. This has been Holyfield Physics TV. I'm Richard Gould. Thanks very much for listening and watching. Work hard, do well in your exams.